In this part of the course Chemistry 2, we are going to solve this exercise, which is about the application of the first law of thermodynamics on an ideal gas. Exercise 2. We have here a sample of this given mass that is put through the following cycle. First step, reversible diabatic compression. Second step, isochoric cooling. Third, isothermal expansion, and the last one, isobaric compression. As usual, we are going to determine all the state variables of each state, also to draw the reversible cycle on a PV diagram, and we finish by calculating all these thermodynamic properties. We start first by defining each state. We start by the state A. We have the number of mole of this ideal gas, which is equal to the mass on the molar mass. Here the mass is equal to 80 grams over 39.9 gram mole minus 1, which is about 2.0 mole. Here is the number of moles of this perfect gas. Also, we have the pressure in state A, which is equal to 3 atm. The volume in state A is equal 16.4 liters, and the temperature in state A is equal 300 Kelvin. Now this gas undergoes an adiabatic change as a first step with an adiabatic compression. So compression, it means that the volume decreases and the pressure increases. Here we have the state B. So we'll have pressure B, volume in this state, and temperature in this state. Here the temperature has increased, which is equal to 450 K. After that, the gas goes through an isochoric change, which means that the volume is constant. Here we'll have the pressure in state C, which is the state C, is equal to 4.5 atm. It is a given value. Volume C is equal to volume in state B to determine. Also, the temperature in state C, it is not given, that we have to calculate. The third step, it is an isothermal change, where the pressure, here we have an expansion, which means that the volume increases and the pressure decreases. So here we have the pressure D in state D, we have volume in state D, and the temperature in state D. Here it is an isothermal change, which means that the temperature in state D is equal to the temperature in state C. And the last one, it is isobaric change. If it is isobaric, it means that the pressure in this state is equal to the pressure in A, which is equal to 3 atm. Now, as a first step, we have to calculate all these state variables. We start from the state B. Here, the state B, we have an adiabatic change. To determine this value, we have just to determine the first one. After that, we'll use the perfect gas equation. Because it is adiabatic, we have the choice between different relationships. It is a reversible adiabatic change. We have P V gamma, which is constant. Here we have P and V are given for A, but for B they are unknown. So I can't use this relationship. But I have another equation which is equal to T V gamma minus 1. is equal to constant. Here I have the both value, and here we have only one, so we can determine this value. So we can write this T A V A is equal to T in state B, V in state B. Now I can determine the volume in state B, which is equal VA gamma minus 1 T in state A over T in state B, and V is equal to VA times TA over TB 1 over gamma minus 1. So we have just to replace by each value. Here we have 16.4, here 300, 450, and here to the 1 over 0.66. And once these values are plugged into the calculator, we get a value of 8.87 liters. So I write it here. 8.87 liters. Now PB can easily be determined because P inside B is equal to nRT over V inside B, which is equal to 2 times 0.082 times 450 over 8.87, and we get a value here of 8.32 ATM. I said 8.32 ATM. Now let's move on to the state C. Here we'll determine the temperature in this state. It is determined from the perfect gas equation. It's equal to P and V in state C over N and R is equal, here we have 4.5 times, here because it is isochoric change, so we have the same value, the same volume, times 8.87 2 times 0.082, and we get a value of 243 Kelvin. Now for state C it is calculated. Now for state D, here we have isothermal change, which means that the temperature in state D is equal to 243 Kelvin, and for the volume is obtained from the perfect gas constant, 2 times 243 over 3 ATM. Here we get a value of 13.3 liters. So there are all the state variables for each state. Now we can draw the PV diagram. We can draw it like this. It is a schematic drawing. It is not exact. So we have here P and V. The highest volume is 16.4, which corresponds to the volume in state A. And it has the highest volume, it has the lowest pressure, 3 atm. It corresponds also to the pressure in state A. So here is the spot of A. Now the gas will undergo a compression, which means that the volume will decrease to 8.87. Here we have the state B. It will reach the highest pressure, 8.32 atm. So we have this spot B. So it is adiabatic change. After that, from B it will go to the state D through isochoric change. Isochoric change, it means that the volume remains constant to a pressure of 4.5 atm. Here we have C, and from C it will undergo isothermal change to a state D. In state D we have the same pressure as A. Here we have D, and it will return to the initial state through isobaric change. Here is D. So we have A, B, C, and D. So first step, second, third, and fourth. Here is the thermodynamic cycle of this perfect gas through the 4 steps. Now, as usual, we have to determine the thermodynamic properties for each step. So it's better to draw a table like this, and we'll fill it each time that we have calculated the thermodynamic properties for each step. We determine all the value in kilojoules. Step 1, step 2, step 3, and step 4. And also we have to verify the first law by calculating the sigma, or the sum of all the function throughout the cycle. Here we have work, heat, also we have internal energy, the change in internal energy, and the change in enthalpy. Let's start from the first step. First step, it is an adiabatic change. Here we have the work for an adiabatic change is equal to N C sub V delta T. We know that gamma is equal to Cp over Cv. And we have a second equation, Cp minus C sub V is equal to R. So we replace here gamma Cv, that is equal to Cp, in this equation. So we get C sub V gamma minus 1 is equal R. So C sub V is equal R over gamma minus 1. Here R is given in 831 joule Kelvin mole. And we get a value of 12.6 joule mole minus 1 Kelvin minus 1. And Cp is equal gamma times Cv, and is equal about 21.0 joule mole minus 1 Kelvin minus 1. So here we replace for the work 2 times 12.6 times 450 minus 300, because here we have T in state B minus T in state A. And here we have, here it is positive, so we get a value of 3.78 kilojoules. Here the heat exchange is equal to 0 because it is an adiabatic change. We don't have a change of heat with the surroundings. The change in internal energy is equal to the work, which is equal to 3.78 kilojoules. And the change in enthalpy is equal to Ncp delta T. So here we replace 2 times 21 times 450 minus 300 Kelvin, which is equal to 6.30 kilojoules. There are these values. So we can fill the first column here. We have work, which is equal to 378, heat 0, 378, and 6.30. Now let's move on to the second cycle, or the second step. Second step, it is isochoric change. In isochoric change, we have the work is equal to minus P delta V is equal to 0. Q is equal to N CV delta T, which is equal to times 12.6 times. Here we have the temperature, final temperature 243 minus 450. It will be negative value, which is equal to minus 5.222 kilojoules. Now the change in internal energy is equal to QV and is equal to minus 5.22 kilojoules, and the change in enthalpy is equal to NCP delta T, which is equal to 2 times 21 times 243 minus 450 Kelvin, and is equal to 8.69 kilojoules. So now we can replace each of these thermodynamic properties in the table. So work is 0, Q is minus 5.22, the same thing here, and here we have minus 8.69 kilojoules. Now the third step, which is isothermal change. For isothermal change, the expression of work is as follows. Normal logarithm V in state D over V in state B. So we have here minus 2 times T1 times 243 times log. Here we have 13.3 liters. Volume in state B is equal to 8.87. And here we get a value of minus 1.64 kilojoules. Here the heat, but before to talk about the heat, it is an isothermal change, and because the internal energy depends only on the change in temperature, therefore here the change in internal energy is 0. And because the first law states that the change in internal energy is equal to the sum of the work plus heat equal to 0, therefore the work is equal to minus heat. Therefore here it will be equal to 1.64 kilojoules. And the same thing here for the enthalpy, it depends only on the change in temperature, so it will be 0. There are the two values, 164 and 1 minus 164 for the work. So we go to the table. Here we have minus 1.64. Here we have 164, 0, 0. Now let's do the last step, which is an isobaric change. Here we have the expression of the work is equal to minus P delta V is equal to minus 3 ATM. Delta V is 16.4 minus 13.3. However, here it is in ATM and here it is in liters. We have to change or to convert to kilojoules, because we know that 1 ATM liter is equal 101.325 joule. So here I will multiply by this conversion factor. But because we are working with the kilojoules, it's better to write the value in kilojoules. So now we can simplify. At the end we get a value in kilojoules, which is equal to minus 0.94 kilojoules. Now the heat Q is equal to NCP delta T is equal to times 21 times 300 minus 243 Kelvin, and here it is equal to 2.39 kilojoules. And the change in internal energy is the sum of W plus Q is equal to 2.39 minus 0.94 and is equal to about 145 kilojoules, and the change in enthalpy is equal to QP and is equal to the same value here, 2.39 kilojoules. So we have determined the delta H, change in internal enthalpy or energy, the exchange heat, and the work. Now we have to fill the last column. Here we have minus 0.94 and the fourth step, here it is 2.39. Here the same thing, 2.39, and here we have 1.45. Now, once we have finished or we have calculated all these thermodynamic properties, now we have to verify the first law. Because work and heat are not state function, therefore they must be not equal to 0, the sum. But instead we have to find that the cyclic work is equal to minus cyclic heat. They have the same value but opposite in sign. If we add this value, we'll find the value of 1.2 kilojoules. And here the same thing, it must be in opposite sign to the work. The same thing here, we have 1.2. Therefore, we have verified this relation. Therefore, we can say that the internal energy of this cycle is equal to the cyclic work plus the cyclic heat, which is equal to 0. So we can verify here that it is 0, and the same thing for the change in enthalpy for the cycle. It is also equal to 0 because both of these are state function. So now we can say that the first law of thermodynamics, when applied to the change of the perfect gas through reversible cycle, is verified.